Okay, so this is a series of videos that cover the nervous system. This is perhaps one of the hardest sections for students to get kind of a handle on, kind of look at some of the different aspects of it. So one of the things we have to understand in order to understand how the nervous system works is how electricity is moved through it. And really, electricity just equates to the movement of charged particles. And really what we're doing for electricity in the human body is we're moving charged particles, that would be ions, from one side of a membrane to another through channels. And in order to kind of understand how that works is we have to understand where the various concentrations of different constituents of the ions are. So here's an example of the two more common ones. In the extracellular fluid, sodium has a very high concentration. As you can see, it's 145 millimoles outside and only 15 millimoles inside. So it's about a 10-to-1 concentration difference, where sodium is higher on the outside and lower on the inside. Conversely, if you look at potassium, that's the K+, notice it's 150 millimoles inside the cell and only 5 outside. So that's about a 30-to-1 concentration from inside to outside. And just to kind of look at what would happen is if we opened a sodium channel, sodium would diffuse down its gradient from a high concentration outside to a low concentration inside. However, potassium, even though it's still a cation, even still it's got a positive charge, if we opened a channel for potassium, it would diffuse from the inside of the cell, because that's where it is in the highest concentration, to outside. Those directions of movements are based on the chemical differences. And those chemical differences, the difference in the concentrations, come from the sodium-potassium pump. So remember, we talked about primary active transporters before. And we're looking at the sodium-potassium ATPase, or sometimes known as the sodium-potassium pump. It's the primary active transporter that's located within the cell membrane that directly uses ATP. And what it does is it pumps 3 sodium out for 2 potassium in. One of the consequences of that is, as we move 3 positive charges out of the cell and only 2 positive charges inside, the cell is going to become more electrically negative. Very similar to your checking account, is if you spent $3 for every $2 you made, it would be in a negative situation, right? You wouldn't have any money, you would owe money because of that. That difference in the concentrations then between the sodium high outside and the potassium high inside is maintained by the sodium-potassium pump, and that's called the chemical disequilibrium. Students often have trouble with this term, but it's pretty simple. If I asked, okay, if sodium were in equilibrium across the cell, everybody would say, oh, well, that means the concentrations are the same. Well, if the concentrations aren't the same, that means sodium is in disequilibrium. And that disequilibrium, where sodium is higher outside the cell than inside, or the disequilibrium for potassium, where potassium is higher inside than outside the cell, is maintained by the sodium-potassium pump. And again, that's that active transport mechanism that allows us to move 3 sodiums out for 2 potassiums in. Very important, especially in terms of muscle and nerve cells. The next slide is going to look at the chemical and electrical gradients based on the movement we just talked about. So in this first part of the figure, we're going to look at a hypothetical cell. And in the cell, we basically have a situation where we have a membrane that separates the inside and outside of the cell, the 2 sides of the cell. The inside of the cell here is shown in the tan color, and the outside is shown in the blue. If you look at the inside has a high concentration of potassium. Again, about 140, 150 millimoles is what we see in the human body. And what's going to happen is potassium, which is represented by the diamonds, right, has a high concentration on the one side. And if you look at the outer chamber, the potassium has about a 5 millimole concentration. And so looking at that, the potassium is going to diffuse through the potassium channels, right? Remember, channels are specific, so only potassium will move through in this case, because we're only looking at the potassium channels. And as potassium moves out, we're going to be taking positives. Remember, potassium is a cation, right? Positives from inside the cell to outside the cell. And as we remove those positives, the inside of the cell becomes more negative relative to the outside. Okay? The magic number that we're going to have to remember, which we're going to kind of explain in a minute, is minus 90 millivolts, and that's the equilibrium potential for potassium. And what happens is, potassium is going to move down its concentration gradient from inside to outside. And as it begins to move, the inside of the cell, as we said, becomes more negative. The cell is more negative because the positively charged potassium ion, that cation, is moving from the inside of the cell to the outside of the cell through these open potassium channels. Now, what happens on the inside is interesting. The potassium has a huge gradient in terms of the difference between the ion concentrations. And again, just to kind of look at 140 millimolars, that's 0.14 moles, which would be about 15%, 14% of Avogadro's number. So about 14% of 6.022 times 10 to the 23rd. So that means basically there's about 9 times 10 to the 22nd ion concentration in terms of the cell. So the point being, there's a lot of potassium ions. And so moving a few across the membrane doesn't change the concentration at all, for the most part. And so there's always going to be what we call a chemical gradient. The chemical gradient for potassium is out of the cell, down its concentration gradient. As we start to do that, we build up what's called an electrical gradient. The electrical gradient is the charge on the inside of the cell. And the electrical gradient as it builds up on the inside, becomes more and more negative. And the reason it does that is because we're removing positive potassiums from inside the cell to outside. But what happens is interesting. Now that we have an electrical gradient that is negative inside and a chemical gradient that's positive moving out, right? Then they oppose each other. And I think we all know that opposites tend to attract. So the oppositely charged, positively charged potassium ion is actually going to tend to now stay in the cell because the electrical gradient, the negative charge, is equal and opposite. And through the process of what we call electrostatic attraction, the positively charged potassium ions are eventually going to be held inside by the negative charge of the cell. When that happens, that's called the equilibrium potential. And the equilibrium potential for potassium, here's a number you ought to memorize, is minus 90 millivolts. So the equilibrium potential is defined when a cell is permeable to one and only one ion, and the electrical gradient is equal and opposite to the chemical gradient. So there's no net movement of the ion. So that's where the word equilibrium potential comes from. And it has to do with a couple different factors. What's the charge of the ion? In this case, it's potassium. What's the direction of movement of the ion? In this case, it's moving from inside the cell to outside the cell. And what's the concentration difference? The larger the concentration difference, that would be the larger chemical gradient. You would need a larger electrical gradient to be equal and opposite. We'll kind of see that in the next example. So we can also look at another type of hypothetical cell, this time really just worrying about the sodium ions, because we have sodium channels open. So in this case, in the outer chamber, we have a higher concentration of sodium outside the cell than inside the cell. So this is fairly similar to what happens in the human body. Again, it's about a 10-to-1 ratio with sodium higher on the outside than the inside. If we open a channel for sodium, sodium is going to diffuse from outside the cell across the channel to the inside of the cell down its concentration gradient. Remember, sodium is a cation. It's a positively charged ion. So as it moves through, it's going to put more positive ions inside the cell. As those positive ions come inside the cell, the inside of the cell is going to become more and more positive. So we start to bring the electrical gradient. Okay? In this case, the electrical gradient, you can see the positives inside are building up because the positive sodium is moving into the through the channel into the cell. As the cell becomes more and more positive, it has an equal and opposite, I guess not opposite, an equal charge that it tends to inhibit sodium from coming in at a certain point. And that's because of a concept which is similar to electrostatic attraction, but in this case it's electrostatic repulsion. Since we're trying to move a positive sodium, right, a cation, into the cell, which is becoming more positive, that same charge repel each other, and it gets harder and harder to move sodium into the cell. At some point, it's called the equilibrium potential again, when the chemical gradient, the concentration difference for sodium moving in, is equal and opposite to the electrical gradient, trying to push sodium out because it's positive inside the cell. There's no net movement of sodium into the cell anymore, and that's called the equilibrium potential. That occurs at a positive 62 millivolts. It's positive because the inside of the cell is more positive than the outside, and it occurs at 62 millivolts because sodium has a lower concentration than potassium. So I have less of a chemical gradient. It's a lower concentration difference. So I have less of a chemical gradient, so I need less of an electrical gradient pushing back. So another number, we'll just round to make it easier, and we'll say the equilibrium potential for sodium is positive 60 millivolts. And again, equilibrium potential is defined as when a cell is permeable to one and only one ion, and the chemical gradient is equal and opposite to the electrical gradient, so there's no net movement of that ion. So again, two things to learn. The equilibrium potential, you should memorize those, and often represented as just an E for equilibrium potential, and then the subscript of whatever ion you're looking at. So the EK, the equilibrium potential for potassium, is minus 90 millivolts, and then the equilibrium potential for sodium is positive 60. One of the important concepts to remember then is that this whole thing works because of the sodium-potassium pump. That creates the disequilibrium, that creates the difference between the concentration of sodium outside the cell and inside the cell, where sodium is higher outside than inside, and at the same time creates the opposite for potassium. Potassium has a higher concentration inside the cell than outside the cell. As a matter of fact, when you think about cells, the ion that is the only one that's opposite of the other ones is potassium. Potassium is the most abundant intracellular cation. It has a high concentration inside the cell, and it's the only one that does that. The other ions that we're going to worry about all have higher concentrations outside the cell in the extracellular fluid. Okay. Now, we can look at another potential. It's called the resting membrane potential. and it's minus 70 millivolts. So again, if you look at this graph right here, you have the equilibrium potential for sodium at positive 60, the equilibrium potential of potassium at minus 90, and you see that this minus 70, it says VM, that's the resting membrane potential. So voltage in the membrane is what it stands for at rest. So that for a nerve cell, and pretty close for a muscle cell, we're going to assume about minus 70 millivolts. Okay, so to kind of look at this figure a little different, looking at these numbers, if by definition the cell were only permeable to potassium, right? The equilibrium potential would tell us that the membrane being only permeable to potassium means it's permeable to one and only one ion, and eventually that ion would stop moving at the membrane potential of minus 90 millivolts. So by definition, at equilibrium potential, the cell is permeable to 100% sodium. So the only ion channels open at that time are for sodium. Likewise, if you go to the other extreme and you looked at if the cell were having a membrane potential of plus 60, by definition, since plus 60 is the equilibrium potential for sodium and a cell were permeable to only sodium, it would have an equilibrium potential of positive 60. So looking at the membrane voltage in normal nerve cells, and again, pretty close in muscles, the equilibrium potential, the membrane potentials, not the equilibrium potential now, the membrane potential at rest is minus 70 millivolts. So if you look, you'll see that we're much closer to the minus 90 than we are to the positive 60, which means the cells, when they're at minus 70, are primarily permeable to potassium and only slightly permeable to sodium. So what determines the resting membrane voltage to a large extent is what is the relative difference between the open and closed ion channels. And so if we just considered sodium-potassium and its effect on membrane voltage, the higher percentage of sodium channels that are open relative to potassium, the higher the membrane potential will be, the closer it will be to positive 60. If we look at the situation where there's a higher percentage of potassium channels open than compared to sodium, then it'll be closer to minus 90. And in fact, if 100% of the potassium channels were open, by definition, we'd be at minus 90. And if 100% of the sodium channels were open, with no potassium channels open, we'd be at its equilibrium potential, positive 60. So by looking at the relatively low membrane voltage at rest, it tells us we're mostly permeable to potassium and only slightly permeable to sodium at this point in time. And that's determined again by the concentration gradients, which are maintained by the sodium-potassium pump, and the relative permeability of the ions, so basically how many ion channels are open for each ion in question. The other point of this slide is for you to remember that neurons have a resting membrane potential that's approximately minus 70 millivolts.